A star roughly 25 times the Sun's mass brightened, faded, and then seemed to disappear. What remained may be the aftermath of a supernova that never truly exploded. In a spiral galaxy called NGC 6946, roughly 22 million light-years away, astronomers watched a point of light do something that a massive dying star was not supposed to do. The source, named N6946-BH1, had been visible in archival Hubble images. In 2009 it brightened to more than 1 million times the luminosity of the Sun for a few months. Then it faded. No brilliant supernova announced the destruction of the star. Later images showed that the optical source had become at least 5 magnitudes fainter than its progenitor. There was still a weak infrared glow, but the star itself seemed to be gone. That sequence made N6946-BH1 one of astronomy's most compelling failed supernova candidates, a possible case in which a massive stellar core collapsed into a black hole while the expected explosion failed. The evidence is remarkable. It is not yet a direct photograph of a black hole being born. Most searches for stellar death look for sudden light. A conventional core collapse supernova begins when a massive star can no longer support its core. Collapse releases an enormous amount of energy, and an outward shock may tear through the star, ejecting material that becomes dazzlingly bright. A failed supernova search reverses that logic. Instead of asking which star appeared, it asks which established star disappeared. The Large Binocular Telescope survey repeatedly imaged nearby galaxies, comparing their luminous evolved stars across years. A missing source could be a detector problem, ordinary variability, dust, or a merger, so disappearance alone is not enough. But if a massive star undergoes a modest transient and then stays dramatically fainter across optical and infrared observations, the absence becomes data. N6946-BH1 emerged from that survey as the strongest candidate. Astronomers were trying to observe an ending defined not by a cosmic flash, but by a light that never returned. Before the event, archival Hubble observations from 2007 showed a luminous red source. Modeling identified the progenitor as a red supergiant with an estimated initial mass of about 25 suns. In March 2009, the source entered an optical outburst. It reached roughly 1 million solar luminosities, bright enough to be unmistakable but weak compared with a normal luminous supernova. The visible transient lasted for months, while a coincident infrared source brightened and evolved more slowly. Afterward, the optical light collapsed. This was not literally a star blinking out in an instant. It was a measured sequence assembled from different telescopes and wavelengths, a massive red star, a comparatively weak outburst, a steep decline, and a faint residual infrared source. That distinction matters because every stage constrains what could have happened. A surviving star hidden behind newly formed dust should still radiate its energy somewhere, even if visible light could no longer escape directly toward Earth. Hubble supplied the most arresting comparison. Images from before the outburst contained the progenitor. New Hubble images taken in 2015 found that it had dramatically faded in visible light, by at least 5 magnitudes. The team also used the Large Binocular Telescope for a long optical record and NASA's Spitzer Space Telescope for infrared measurements. Spitzer detected declining mid-infrared emission, while Hubble found faint near-infrared light at or close to the original position. Those traces are important because dust absorbs visible radiation and re-radiates energy in the infrared. If the star merely wrapped itself in a dusty shell, the missing optical luminosity should not simply cease to exist. The researchers modeled such possibilities and found the late-time energy output much lower than the progenitors and still declining. The multi-wavelength evidence did not make alternative explanations logically impossible, but it made a quietly surviving, dust-hidden star increasingly difficult to reconcile with the observations. The proposed mechanism is stranger than simple disappearance. When the iron core of a massive star collapses, enormous energy escapes in neutrinos. That energy loss slightly reduces the gravitational mass at the center. In a red supergiant, the loosely bound hydrogen envelope may respond to that sudden change by moving outward and becoming unbound, even if the deeper collapse does not launch a successful supernova shock. Models predict a cool, relatively faint transient powered as the expelled envelope expands and recombines. Meanwhile, much of the star's core can continue inward and form a black hole. Some remaining material may fall back and feed the new black hole, creating an accretion flow that emits weak, fading infrared light. N6946, BH1's 2009 outburst and later infrared remnant are broadly consistent with this picture. Yet consistency is not identity. Astronomers infer the compact object through the fate of the light around it, they have not resolved an event horizon at that distant location. Researchers tested less exotic ways to lose a star. An eruptive star can eject dust and hide itself. A stellar merger can produce a luminous red transient and leave a dusty remnant. Some unstable massive stars undergo eruptions called supernova imposters without destroying their cores. The 2017 paper compared the observed spectral energy distribution and its change over time with these alternatives. A thick expanding dust shell could suppress optical light, but the surviving star's energy should be reprocessed, and the infrared behavior did not supply the lost progenitor luminosity. The remaining bolometric luminosity was estimated to be more than 6 times fainter than before the outburst and was decreasing. The authors concluded that a dusty survivor, an imposter, or a merger was unlikely, while failed core collapse fit the overall pattern. They also stated what further evidence was needed: continued infrared and X-ray observations. Scientific restraint is part of this story. The best explanation can lead without becoming a confirmed observation. Why would a failed explosion matter beyond one missing point? Astronomers have long noted a shortage of directly identified high-mass red supergiant progenitors for ordinary Type 2P supernovae. One possibility is that some massive stars do not make luminous supernovae at all. Quiet collapse could also help form relatively massive stellar black holes because a successful explosion does not first expel as much of the star. During the first 7 years described by the survey team, N6946, BH1 was the only likely failure while 6 normal supernovae occurred in the monitored galaxies. From that small sample they offered a preliminary failed fraction of roughly 10 to 30% among massive star deaths. That range was not a final census, small number statistics and selection effects matter. Its importance was motivational. Even one credible vanishing star showed that surveys built only to count bright explosions might miss a physically important path to black hole formation. The label direct collapse can sound cleaner than the event probably was. It does not necessarily mean every layer fell inward without any display. N6946, BH1 produced a measurable outburst, and models allow the hydrogen envelope to be weakly ejected after neutrino mass loss. Failed supernova means the core collapse did not drive the familiar energetic, luminous explosion, not that absolutely nothing escaped. Nor does the name N6946, BH1 prove a black hole exists, it identifies the candidate. The observations show a massive progenitor, a low-energy transient, profound optical fading, and weak infrared emission. The black hole is the physical interpretation connecting them. This careful wording protects the most interesting fact from exaggeration. Astronomers may have recognized the birth of a dark object mainly because a luminous object stopped accounting for itself. The unsettling part is not that a star can die. It is that one of the universe's most violent transformations may leave so little notice. A successful supernova can outshine its host galaxy and scatter newly made elements across space. A failed explosion may offer months of muted light, a diminishing infrared ember, and then an absence that only years of earlier images can reveal. N6946, BH1 remains a candidate, not a closed case. Its history was reconstructed by comparing what telescopes saw before, during, and long after the outburst, and by asking where the progenitor's energy could have gone. If future observations confirm the failed collapse interpretation, the event will represent a rare empirical bridge between massive stars and stellar black holes. If another explanation wins, the search method will still have exposed how difficult it is to inventory deaths that do not advertise themselves. Somewhere in a crowded galaxy, a star may have become a black hole almost in silence. The open question is how often the sky has done this without anyone looking at the right missing light.